So glad to be able to join this series. I know you're all doing awesome work here in the Business School of AI and happy to contribute. So I've been a technologist for over 22 years and worked in every role in the world of technology. I started off as a developer. I did product management for some time, and the last 10 years I've been a technology executive, basically leading engineering teams and right now leading data science teams as well. Last 3-4 years back, I think 4 years back, I was very curious to learn about machine learning and its applications that are practical. So got involved in a number of projects. Some of the highlights include lung cancer research for Roswell University Park Hospital, and more recently with Veterans Affairs to calculate the risk of suicide of veterans using machine learning, and also natural language processing to create a COVID-19 screening bot. So I will be covering a few of those use cases I've worked on today, apart from other use cases in healthcare. Apart from all these roles, I also do a lot of volunteer work. I am a lead member of the AI Working Group, which is a collaboration of federal, industry, and academia. And through that working group, I co-authored the AI Primer, AI Playbook, and more recently, Ethical AI Framework to help US government adopt AI and evaluate ethical outcomes of AI. I also am a Women in AI ambassador. Women in AI is a nonprofit that's based out of France. It has members from over 100 countries, and to support its mission, I organize Women in AI events. I also mentor girls from middle school to high school, as well as mid-career women into how to pivot into AI or any other technology related challenges. And right now, I'm happy to say that I am writing a book on ethical AI under Manning Publications. I have a contract and the book is coming out in the spring, summer of 2022. So that's keeping me busy these days. So that's in a nutshell about my journey and involvement in AI and machine learning projects. So let me share my screen to talk a little bit more about some of the use cases I have worked on, some of the use cases I might be working in the future as well. Can you all see my screen?
Yeah.
Awesome.
Yep.
And like Ananya, yes, Ananya.
Hi, Swathi. Yeah, I would just like to request, other than, in addition to your presentation, if we could also understand the life cycle of the AI product, the process of like getting the data to like feature engineering and then actually releasing it to production. I mean, just to give a technical tint to it as well.
Yeah, I have covered it as part of the use case as well.
That would be awesome. Yeah, thank you so much.
Yeah, of course. And like Ananya mentioned, I host the AI ML show on YouTube, so feel free to subscribe. I do interview people working actively in the field of AI. Like I have interviewed a lot of AI ethicists. I've also interviewed practicing data scientists and researchers and others. So feel free to watch any of the topics that interest you. So this is a little bit about myself, which I have already spoken about. So we notice in the last few years that healthcare providers are actually looking at AI-powered solutions today. Why? Because they want to support decision-making and mainly to improve patient outcomes. Of course, there is the efficiency and reduction of cost, which comes as a byproduct of actually focusing on improving patient outcomes. And some of the examples I'll share with you today will help you understand that. So the very first example I want to share is image analysis. Two use cases are is diabetic retinopathy. You might have read research papers about image analysis using machine learning for early detection of the eye disease called diabetic retinopathy. And the second use case I want to cover, this will be the in-depth coverage of lung cancer research that I was personally involved in leading the team, strategizing the solution, and so on and so forth. So starting off with the lung cancer research use case, it was known and all the inputs or the problem statement or the hypothesis of the problem actually was given to us by a lung cancer surgeon. As a data scientist, I do not qualify to know what are the problems that exist in any healthcare area. So this is where it's essential to have that subject matter expert come and have that conversations with us about what are the problems they're trying to solve. As we are good in determining how to solve the problem using machine learning, they are the best person to determine how to improve patient outcomes. So it started off with a conversation with a lung cancer surgeon from Roswell University Park Hospital, who said that there is a hypothesis that the visceral and subcutaneous fat actually adversely impacts patient recovery from lung cancer, as well as increases the chances of mortality. And previously, there was an assumption that there is no correlation between BMI, the body mass index, and lung cancer. But what some of the doctors did some research, and the preliminary research showed that they had to go one level deeper. So the visceral and subcutaneous fat that is deposited inside the body, the ratio actually adversely affects the lung cancer patient outcomes. So the next step the lung cancer surgeon told us is that today, the radiologists are actually taking the CT scans and actually going and detecting the visceral and subcutaneous fat. And the way they do that is that they take each CT scan and manually go and locate the L3 vertebrae of the spine. And from there, they measure the visceral and subcutaneous fat using a small program called ImageJ. And that takes a few minutes for each CT scan for the radiologist to actually measure. And what we did as the next step is actually we had a call with the radiologist, and the radiologist went through the manual process and we recorded it for help with our machine learning algorithms and with our teams even. In fact, our team wasn't even formed, the team of data scientists, when we actually had that conversation. So recording that session with the radiologist really helped. And then obviously our problem statement boiled down to two factors. Given a CT scan of a lung cancer patient, locate the L3 vertebrae. Number one, use machine learning to locate the L3 vertebrae. And number two, measure the visceral and the subcutaneous fat. So those were the problem statements, and that was the background how we came about with the problem statement. So as Ananya mentioned, I will go through, of course, I don't have a diagrammatic representation here, but in any machine learning solution or problem we are trying to solve, there are a couple of steps. Number one, I emphasize on the business objectives. So here, if the lung cancer surgeon and the radiologist did not have a conversation with us, we would not even know about the business process or the current process. So it's very crucial to take a step back and have that conversation with a SME or a subject matter expert or a domain expert. Because as technologists, most of us know our technologies, but not necessarily the business process of the industry. Even though you have been working in healthcare or finance sector, unless you speak to the business process owners, you wouldn't understand the business flows, the business policies that went into making those business flows, and so on and so forth. So I emphasize a lot on the business process owners conversation, as well as the objective and the problem statements. because based on the problem statements, sometimes the machine learning algorithm output might or might not be a good fit, because if you're making, for example, a diagnosis, if it is like 93% accuracy, is it an accuracy that you can live with? Is not a question you can answer, but again, you only after speaking to a doctor you can answer. So that's the first step. You make sure you have your business objectives clear by speaking with the business owners. Number two is data. So the crux of any machine learning algorithm, and I would take it a step forward and say not just machine learning, reinforcement learning, robotic processes, everything depends on data, because even for the robot to see where the path is, it uses image recognition software and so on and so forth to see. So it's all based on data. So the next step of any machine learning project is the data. First of all, you identify where your data comes from. Secondly, you ensure that the data is de-identified, so there are no ethical AI issues. I know Sudha recently had an ethical AI, I think, a webinar with Dia. So you're all aware. So you want to make sure that box is checked. The next step that takes most
we actually had a career pivot to AI ethics as a 6-hour online course over 3 weeks. So I'm seeing some of my AI ethics course students here. We also did a capstone AI lab course. All our courses are like 6 weeks live online. And so we have a mix of students who understand this data science cycle. And then we also have the AI ethics students. So it's perfect what you're talking. And this is the first time I'm hearing somebody talk about building AI as a data scientist who's incorporating ethics in it, honestly. So I love it. Thank you.
Yeah. So that is my, I think, pet project is evaluating the ethics and bias at every step of the process. And that's why I'm grateful for the opportunity to write a book on that. So yes, so that's one step in the data process, but the majority of the time in all the projects that I've been involved in is the analysis of data. So if you given 1 million records or more than 1 million records, your data analysis is so important, because data is dirty. Data has bias. Data has a lot of things that you don't want it to have. You wish it was clean, but it's not. Data will have like records that are missing, that records that have null values, records that don't make sense. Sometimes I have seen, especially with the veterans recent project we did this year, Veterans Administration issued the tech challenge for determining the risk of veteran suicide. And we were given synthetic data, and most of the data was junk. Junk literally, like age had minus 7.5 as a value. So data, you wish it was clean, but the data given usually, even whatever be the source of data, usually has a lot of things that you have to think about. And sometimes even understanding the data. Another use case that I will be covering today, which includes correlation between lung cancer surgery as well as readmission back to the hospital. There, we couldn't even understand the data. It had so many medical codes. Obviously, ICD-10 codes are universal, but it had more codes that we had to have almost weekly conversations with the lung cancer surgeon to understand. So if you're not from the domain, especially some specific problems will be only understood after the domain expert explains to you, because we have to make a determination sometimes for huge data sets, which are millions of records with 1,000 variables. Your accuracy can get very diluted if you include variables that you do not want to be included or doesn't make sense to the problem statement. And I will be covering examples in the later use case. So the data analysis is the time that takes the bulk of your machine learning projects. And then the modeling is actually the easy part. Machine learning modeling, once you run your model, you see your accuracy, precision, and recall, and then you always come back And you might have to do your data analysis again as an iterative process if you don't get accuracy or that you are expecting. The only way to improve accuracy is either you do data analysis again and some feature engineering. So data analysis is also called feature engineering because basically the variables are nothing but the features of a record. And we call it feature engineering because you do something with that feature. Either you drop the feature or you edit the feature or you modify and augment the feature and so on. So data analysis is also another component of data analysis is feature engineering. But before that, you also have to do your exploratory data analysis. What that means is you might want to see what does the graph of the data looks like, what percentage of the data are maybe gender, what percentage of the data are male versus female, or what percentage of the data resides in a particular geographical area like state, rural or urban, and so on and so forth. So you might want to do what is called the exploratory data analysis as well. And typically in a fraud detection use case, your exploratory data analysis will reveal very soon what percentage of the data has fraudulent transactions versus non-fraudulent. Usually fraudulent transactions will be lesser percentage, right? You don't, it's not every day that your credit card is being stolen and being actually fraudulent transactions taking place. So in that case, the data distribution is very skewed and there are different ways to normalize the data. So that's part of the data analysis as well. And then we go to the modeling, which is writing the machine learning models. And depending on the problem you're trying to solve, it could be a classification or a regression model. Or sometimes if it's image analysis, we are using the CNNs like this example here. So with this example, I forgot another important point. Whenever we start with a machine learning problem, one of the first things data scientists do is read related research papers, because mostly there would be some research paper already written in that area that you're trying to focus. What that will help you is, one, it can help you identify the publicly available data sets sooner than later. Secondly, it can help you with an actual path how to solve the problem. Sometimes it can help you with an actual open source code, as in this use case that I'm just presenting. We actually took the image processing of medical images and CT scans with an open, we started with an open source code that was available. So essentially here, the publicly available data set is the Cancer Imaging Archive website. But if you go there, you will be confused because it has a lot of repositories, including genomic data, different types of cancer, et cetera, et cetera. So you have to filter down to your specific, in this case, we were looking at lung cancer images, as well as the ones, actually there's no filter, the ones with the vertebrae, but we were looking at the spinal images so that we can use it for locating the L3 vertebrae. And essentially in our data, we found through reading some research papers that there is already a AI open source algorithm called Sarcopenia.ai, which actually uses convolutional neural networks to actually find the L3 vertebrae. So that was our starting point for my team, but it had the code had a lot of issues. It wasn't very organized. It was very, it wasn't written in a step-by-step manner, and initial analysis gave very low accuracy. We got only 57% of accuracy. And we started with about 317,000 records. And one of the things we discovered were the records before 1990, the image quality was very poor. Obviously, the CNN will have more difficulty reading that quality of images. So we actually chose at a later point post 1990 images so that we get better clarity. So essentially, the way the algorithm worked was that it converts the 3D CT scan images into 2D images, because 2D images has that maximum intensity. And then it also, if the CT scan is in different orientation, it makes sure it's frontal, mostly it's frontal, or sagittal. A sagittal view is a medical terminology they use for like left and right planes. So the algorithm initially converts the 3D image into 2D and also changes the orientation of the image. And the team worked on normalizing some of the pixel sizes, because if the different images are different pixel sizes, you really will not get the algorithm to detect the L3 vertebrae. So basically, there were input parameters that we could modify. Like the input parameters was measured in house field units, which is a unit typically used for image files, and those input parameters were modified to figure out how we can get better accuracy. So end of the project, we were able to improve the accuracy from 57 to 76%. And the interesting thing is, after 3 months, actually, I think 4 months, the team was only able to complete the first part of the project, which is detection of the L3 vertebrae. The next part is the detection of the adipose and visceral and subcutaneous fat that is close to the vertebrae. So the team couldn't get to that yet, but it is in our future sprints to get to that. So that was our objective, something that we achieved. And obviously the lung cancer surgeon was happy that we could at least have this kind of accuracy. And with the help of the radiologist can then only verify these images and then give a go or no go, at least for 76% of the cases, compared to the tedious manual process they were doing. So those were some outcomes we achieved. So I'll pause here and take questions before going to the next use cases.
Yes, Swathi, can you hear me?
Yes.
Yes. So yeah, the process of understanding the business problem and business process, I mean, in this case, the medical journey of the manual diagnosis, yeah, super critical in designing your solution. Does the example of the CT scans before 1990 being not that crisply clear, that might be a very common thing. Does that impact, the accuracy? Can that impact the accuracy? And how can we overcome such hindrances even in other use cases, whether it's CT scan or medical records? Can we synthesize any? Can we change the algorithm, like instead of a CNN, RNN? Or, I mean, how do we overcome such limitations in historic medical data?
Yeah, that's a great question. So one of the things that we, in order to improve the algorithm, it's not changing the CNN. The algorithm will only perform as good as the images it can learn from. So first thing is, maybe we collect and give it or feed it enough number of both unclear and clear data sets, but in the unclear, we want to adjust the pixels. So it's a very step-by-step process when it comes to images. First, it has to be converted from 3D to 2D, and then from 2D to it will actually normalize the pixel sizes as well. But again, it's playing with those parameters, what works best. If it is like, for example, for this images, we had to play around 1 millimeter by 1 millimeter pixel size and making sure that it is in the frontal image, so that usually the vertebrae is at the center And so that measurement will make sure that it is accurate. So it's all a trial and error that we play with. And also, how can we get more data? Because sometimes we are constrained, especially with something like this cancer images archive and other use cases I'll be covering. They might only have certain percentage of years of data. And this is when you can work with the hospital. So one thing I did not mention is this algorithm, what our team worked on was outside that hospital data, correct? Because it was the Roswell Park University Hospital who asked us to work on this problem, but we didn't work on their proprietary data. We worked on a publicly available data set. And what we did is we gave back our algorithm. And obviously they did not have strong internal data scientists, but we said, hey, just execute. We gave an executable file for them to run it on some internal files that they have. The other interesting thing, and I have not yet worked on it, is what is called federated learning that has become very popular recently. Federated learning will not only help with privacy concerns. Say, for example, we don't want to use Roswell Park's current patient data outside Roswell Park. What federated learning will do is establish a separate cloud hosting where two teams can work on the similar problem. And the team inside any hospital can take that algorithm, run it internally, and then give feedback, and externally you can iterate on that. So all those challenges do exist. So I think most hospitals are establishing their own strong data science teams, but there is also an advantage of open source collaboration, of working on similar projects by different teams outside the hospitals as well.
Yeah, I totally agree. Even in the fraud domain that I currently work in, proprietary data, customer data is not easily accessible. So we do have to give them the model to train it themselves. The federated machine learning is definitely a great new platform. I do have a couple of questions in the chat for you. So one Sudha asked, in the data science cycle, where is the business knowledge? Is it with the radiologist or a business user?
It depends on the use case. In this case, the knowledge was both with the surgeon as well as the radiologist, because the surgeon is the driver of the problem hypothesis. The surgeon is the one who's determining. Actually, the whole reason we want to do this analysis and research is that surgeon can take improved treatments once he knows percentage of population has higher visceral fat ratio, then he or she can make different kinds of treatments to improve patient outcomes. So in this use case, the driver is the surgeon, and then the radiologist is helping the surgeon by doing the manual analysis of locating L3 vertebrae and the visceral fat currently. So we are helping both. And again, it depends on your use case. And sometimes it's a rabbit hole. So for example, in the veterans project we worked on, we were supposed to use machine learning to identify the risk of veteran suicide. We were given synthetic data, but we were given one domain expert, but she was more as a psychologist. She did not even understand the data or anything to a large extent. So I had to go through my private network to find out a domain expert who can give us inputs about understanding. There are different levels of suicide categories. And, these are not the things we ever deal with in our daily lives. So sometimes it's a rabbit hole to find the correct data domain expert who will interpret the data for you. But most often, if you're working in an organization, you should be able to access the business users.
Right, absolutely. The subject matter expert or the domain expert is super critical in guiding our data analysis and the modeling. Another question, Rajana, am I pronouncing it right? Sorry if I didn't. Rajana, do you want to ask your question out loud? You have a question on this current slide.
Yeah, thank you, Swathi and Ananya. I'm audible, hopefully.
Yes.
Please make sure that we pronounce your name right. We are very big on.
Yeah, that's right. That's right,
global.
Rajana.
Yes.
Yeah.
Rajana.
Yeah.
Thank you.
Yeah, right. Thank you. Actually, no, I'm just curious to know, like, how the accuracy was improved from 57 to 76. Is it by data augmentation, or maybe what are the technique been used on this? It's really helpful. So
yeah, that's a great question. So essentially, we did a couple of things. The algorithm was written either very quickly or in a haphazard manner. The first thing the team did was separate the pre-processing code and the detection code, because pre-processing, you're right, is helpful in augmenting more images, in actually playing with that normalized view, like I said, within the 1 millimeter on either side of the vertebrae and so on. We also did, I was trying to remember, yeah, we also did the k-fold cross-validation so that we divided the images into multiple units so that we can compare and contrast the accuracy, and when we did the k-fold as well. So those were some of the things that we did. And obviously, I also already mentioned we played a lot with the pre-processing and post-processing parameters. So for example, one of the things we could increase was the house field units, which is basically, house field unit is a measure that used typically in medical images that actually show the depth of the image as well as the intensity of the image. So we played around with the house field unit parameters as well.
okay. Thank you, Swathi. Thank you very much. And also this federal learning, thank you for that. So I'll go through it.
Sure. Ananya, any other questions? Let's see the chat.
Yeah, we have Nicholas. Hey, Nicholas, do you want to voice your question?
Sure, why not? Can you hear me?
Yes.
Yes.
Okay, hey. I'm actually in the car right now, so I actually took my first COVID shot, and I have to be here for like 30 minutes. So I've got 10 minutes left, and I got my wife here with me. She's an aspiring data scientist. But actually, my question was related to the importance of stakeholder collaboration with domain experts, business processes, and all these kind of things. And I think it's Sudha, you heard me talk about this. I think it was last Monday or this Monday, I can't even remember. How is that approached in terms of the tools for collaboration? I mean, is it through emails, is it through Teams chat? You have to be there physically, which of course is a challenge right now with remote ways of working. I want to know a little bit more than that, about that. And then I had another question as well, but let's just start with that one, because I think that you're one of the first ones, not the first ones, but that actually talks about that, about the importance of cross collaboration. So please, if you have anything more to say, again, how that is being addressed with the tools and technologies.
Yeah, awesome question. I would say all of the above, with the exception of in-person. I don't think you need in-person. I would say of all the data science projects I've worked in the last few years, this image processing was one of the most complex ones. And we didn't have to meet the surgeon or the radiologist in person. They were, Roosevelt Park University Hospital is located in upstate New York, in Buffalo, New York. And the team was located mostly in the Washington, D.C. area where I'm located. So I think the medium doesn't matter as long as the clarity is provided by the users. In this case, the recording that we did with the radiologist, where he went through the tedious process of explaining to non-medical people, which is me and my team, the tedious process of explaining the manually how he's doing that step of taking one CT scan. We recorded that and on Zoom, and that was the most useful thing we did, because later on, as we established the data science team, they had to watch the recording, because you're basically automating a manual process. So it was very helpful. So I would say all of the above, and it also depends on use case to use case. The other use cases I'm going to cover didn't involve recording, but it involved more frequent touch points with the surgeon, because we were trying to understand really large quantities of data. So it all depends. Use all the mediums possible, and where possible, depending on the use case, you can do recording. I'm a huge proponent of using collaborative tools like Miro, where multiple people can whiteboard virtually. So I think all of the above.
Okay, perfect.
Awesome.
If you're talking, Nicholas, you're on mute.
I was talking.
You were saying all your good things on mute.
Yeah, exactly. No, it's just praise, Swathi. No, I think, thanks so much for the answer. I'm a big fan of recordings as well, but I mean, since I've been working with digital twins, and recording something both for people where they can explain, but actually also in like taking in the data that you're going to work with and exposing that, I think like the combination is pretty interesting, to be honest. So I would say like the medium definitely matters. And if you approach, that with the most modern tool sets for collaboration, I think you can also accelerate, data-driven decision-making at scale. But anyway, super great answer. And again, like with the recording, that's also what I've been using as well. So you can actually, introduce, onboard new people to the actual problem and letting the domain expert, talk about what it is actually that it's trying to solve. But I had another question as well in the chat, which I can't remember. So if someone can read that question, because I can't access the chat for some reason, I don't know.
Yeah, sure, Nicholas, I'll read it for you. What's the role of industry taxonomies and ontologies that plays in the metadata richness to the data? Okay, so we need the industry taxonomies and ontologies. Okay. Yeah, how do you handle that, Swathi, for enriching the data?
Sure. I think first we need the inputs from the domain expert, and the other use case that I'm going to cover, the third use case today, is a machine learning project I led, where we did the correlation between lung cancer surgery hospital readmissions prediction. In that use case, I think we had multiple calls. That was like, we had the most calls with the surgeon. We had almost on a weekly basis, even if he could spare only 10 minutes, because understanding that data was the most difficult. Whereas here, it was like one time we recorded and it was fine. There, he introduced us to something called the Charleston Comorbidity Index, which was the first time I heard. And it's a very medical term, which actually is an industry term in the medical domain. That is used to calculate the risk of mortality based on over 10-year period of a patient with a bunch of comorbidities that they have. So yes, again, it's the domain expert will give you some inputs, but later on it's the data science homework. We read a bunch of research papers that explains what that index is, how can we best use, how can we use it for augmentation and so on, because in healthcare, the domain knowledge is everything. Even an ICD-10 code can make or break the algorithm if it is important or not important. But again, even if you have worked in the healthcare sector before, unless the doctor, the surgeon, the radiologist, they who are working on a day-to-day basis tell you, it's a little challenge on your own to find. At least they will give you that input initially, then later on we can go and read the research papers.
Fantastic. So I think like it's a people, I wouldn't say problem, but it's like AI is a lot of a people industry still, in terms of then getting to the data side, and then the data is, like you said, right? That's a challenge on its own. But thanks so much for this, Swathi. I really appreciate it. Thank you so much.
You're welcome.
Swathi, I think we have a lot of health enthusiasts here. I mean, including myself. Are there any other slides that you want to proceed on, or?
Yeah, I would love to cover if possible. I know we have 15 minutes, but
Right.
we have only touched the tip of the iceberg. I have a 25, I think this is 25 slides, but three main use cases I was digging deep. I personally worked. The other use cases are what I know in the industry. So this was one use case. The second one is the use case of using natural language processing chatbot for COVID-19 screening, which is pretty much, we used a Google Dialogflow and we used CDC guidelines. This was basically developed early on last summer because that time businesses were shut down from April to June, at least in Virginia and DC area. And then as businesses were reopening around July, they had to fill the paper forms for all the employees and visitors coming into their location. And CDC was obviously, I don't know how it is in California, but even now when I drop my a 5-year-old in the preschool, I have to fill the forms online on the app and they take the temperature and all that. So we basically used a natural language processing engine of Google Dialogflow and created this chatbot assistant that could be enabled on your website, which is mobile optimized and ask the screening questions. And this was very popular. We recently won Health Innovation Award here with respect to agencies as well, the federal agencies. So this is in a nutshell I wanted to cover. The next one I wanted to cover is the lung cancer surgery readmission rates. That was a project again with the Roosevelt Park University Hospital. Basically, readmission after surgery. Any surgery is expensive, but more so in the lung cancer surgery, and can drive adverse outcomes for patients. And CMS actually started penalizing. They formed some committee and they came up with some rules. So as if you have more than 2 or 3 readmissions, they can penalize the hospitals up to 3% of the value they can penalize. And then we had to determine, given the data set, the probability of readmission within 30 days of discharge from the hospital. And we also wanted to find out what are the top factors driving this readmission. So obviously, again, here the data set was interesting. Although HCUP, which is a nationwide readmission data, is maintained by the federal agencies and nonprofits, it's actually data we had to purchase. It was 1,200 for each year. And we purchased 3 years of data, which gave us like 40 million records. But since we said this is readmission after lung cancer surgery, we had to filter the records for lobectomy, which is lung surgery. And it turned out to be 44,000 records. And then we had to filter again for a 30-day readmission, and it turned out to be only 3,000 records. So another example of data analysis, you can start with a large data set, like 40 million over 3 years, but once you apply all the conditions to your problem, it might become a very small data set. And initially we played around with 60-day readmission as well as 30-day readmission. Again, this was based on the inputs provided by the lung cancer surgeon. And the analysis for this took the longest. Like I was mentioning before, even though the record size was small, the variables were a lot. They had like at least 500 variables, and we had to understand in that variable. So if you take a patient, it had all the medical history, the comorbidities, the age, the gender, the way they live, what type of hospital bed, what type of insurance they had. So they had lots and lots of variables. And we had to have multiple conversations with the surgeon to understand these variables. Some are pretty self-explanatory. There's another variable called APDRG, which is basically industry standard in the world of healthcare providers, but we did not know that, what it means, whether it's important or not. And we did a lot of analysis. And then finally, we boiled it down to 100 variables, which is pre and post operative variables. And even then, actually, we used multiple classification methods and went with XGBoost based on the accuracy, precision, and recall. And it's typical like a fraud detection problem. Your readmission might be lesser percentage than your regular, so your data is a little bit skewed, and obviously we have to work on some data normalizing methods. Also, there was a lot of null values. We had to do some data imputation methods. So the analysis took a long time, and then we determined XGBoost was the best due to the best recall, because again, because the data is so skewed, you don't go with accuracy. Recall is a good measure because recall measures the false negatives, and here the false negatives is very important. So, and we found some of the top factors that influence the decision at the end of it. So this was a different kind of problem in the same area.
Hey, Swathi, Suresh here, Swathi. The similar thing, whatever you're telling it about the mortality, right? I'm doing the similar project, morbidity and mortality prediction tool, where it involves PPS, where palliative performance scale, PPS, and also it includes CCI, which you already given the link, charts and commodity index, along with the LACE index, one of the scaling, and also chronic disease score. Based on all the four taking into consideration, I am coming with a prediction mortality rate, which includes 30 days morbidity mortality probability, and also my final prediction column is like 30, 60, and 90 days.
Good luck with that, because one of the other projects I've worked, a correlation between lung cancer, patients with mental illness and mortality. It's what we came to know is like mortality is one of the toughest things to predict, even though there are indices. All the indexes like Charleston Comorbidity Index is based on 10-year time frame. Getting a prediction if someone will die in a 30-day time frame is nearly next to impossible, according to me.
That's I'm taking into consideration. Yeah, I'm taking only consideration length of stays in the hospital, when the admission date, when the discharge date, and when is the death date. Based on 30, 60, 90, I'm classifying it and just predicting that. I do understand, I'm not considering all the variables we need to be considered.
Okay,
and
got it.
See,
Thanks for sharing.
Yeah, good luck. Really good luck, Suresh. It's a very exciting project.
Apart from that, I'm also one of the, it's only initial stage, I'm just gathering it. A CPT, what is that called? C8 and C4 and C8, CD8 and CD4, which is the part of a cells, cancer cells.
That's good. That's good.
It's a part of a claim, I guess. I'm not sure. Still, I'm in the initial stage of gathering the information. Once I start, I may, I may question you so many questions on that.
Yes, Suresh. Yeah, please feel free to connect with Swathi. But at this point, did you have a particular question or for Swathi?
No. If you have anything related to the, cancer prediction or cancer therapy, that would be, if you can share it, that would be great.
Swathi, did you have that in your YouTube channel or book or any paper you published?
No, I haven't actually. Once you post this on the YouTube, I have, because with the YouTube, I wanted to make sure that all the people that I worked with, I have their consent, right? So this is more educational, so I'm doing that over here. But Suresh, to your question, it all depends on the problem statement. Once you know the exact problem statement, you can.
It's like basically immune response from the CAR-T therapy for the cancer patients.
Yeah, I wouldn't be the best person to answer that. I think you should talk to exact domain experts. And on top of that, if you find a research paper with specific machine learning modeling and you have issues.
But I don't see anything related to CAR T therapy, which is new in terms of cancer. I need to check. I need to know what is the results based on that,
Yeah,
sense.
usually one thing I must say, National Science Foundation has all sorts of researches. So go to NSF website. It's like a deep digging into what are some of the things that have been published.
Okay, sure.
Okay. Awesome. Thank you so much, Swathi. I think we do need to wrap up soon. I want to be respectful of your time. But there is one interesting question from Nicholas, actually. So human beings, we get these pathological diseases, but then a lot of our lifestyle throughout our life influences that. Digital twins is Nicholas's angle of question. So if there could be a digital twin of that human being, and if they had a smoking habit in the past or something else, which could help predict the outcome of this current condition, whether it's a lung disease or something else. What are your thoughts on using a digital twin, just like we use for the cars?
Yeah, that's a good question. So essentially, I look at it as the prediction classification problem, along with the factors typical to what I have shown here for the readmission rate, right? So basically, you're based on the history of data of patients who have had lung cancer and the fact that they're smoking, can you predict the probability of somebody getting lung cancer based on the history, right? And it also has other complexities like what are the comorbidities, where are they living, so on and so forth, right? So I'm not the best person to say, if a person living in an urban area and is smoking for the last 15 years, is that person at a higher risk of cancer compared to somebody living in the rural area with smoking the same years? But the data will tell you. So identify your data sets and do the supervised learning classification algorithm. And in the classification, if some of the type of algorithms like XGBoost will give you the top 10 factors affecting your prediction. So that you can basically feed that output to whatever you call as the digital twin.
Interesting. Very insightful. Thank you so much.
Down to 2 minutes, so we need to let Swathi finish up this use case.
Yeah.
I think I've done, like we have done the SG model as the best one and found the top factors that influenced was the age of the person, the Medicare that they had, the wage index. So wage index was basically not like specific index, but it had like based on like, I think it's Census Bureau has wage index, and that was one of the variables that was impacting. So that was the output of the algorithms that we built.
Yeah, if I could squeeze in one last one in the last couple of minutes, we have Bruce here. He's trying to apply AI on postural torsion syndrome. Hey, Bruce, do you want to voice your question?
Swathi, can you get out of sharing your screen so we can see you?
Yeah, absolutely.
Yes, thank you. Thank you.
Hey, Bruce. Okay, or I can just read the question. So Bruce is researching on how to use AI for running a postural torsion syndrome assessment and providing recommendations. He could use some help in identifying the potential AI that could work. Okay. There is a link.
So I'm not from healthcare industry, but I'm seeing a parallel. We did this capstone AI lab as a project here, and we we work with real industry data, with the real industry problem, go through this exercise of how to take the business problem and make it into a problem statement and do feature engineering. And then the modeling itself we do using no-code AI. So the prediction part you're saying, I see a parallel to, outside of healthcare industry. But one lesson I hear from you is go look at research, and healthcare seems to have a lot more lingo.
Yes. That, and also you have to speak to the domain expert, because research might or might not tell you in depth what is the importance of a particular variable. The domain expert, whether it's a doctor or a surgeon, will have more context.
Yeah.
I think with Bruce's question, it's too high level. Build an AI for running. I want to understand. What do you mean by build an AI? Usually our problem statement starts with, can we predict, like, for example, can we automate this image detection in the lung cancer image, or can we predict whether they would be readmitted or not readmitted? So we have to boil it down to a specific outcome.
Yes, just as you described, Swathi, it sounds like for this condition, postural torsion syndrome, I guess he would have to talk to the doctor, the actual different elements for the prognosis, and then come up with that one problem which has enough data, whether it's this image or the doctor notes or something, and kind of boil it down to one use case that can have a high impact. Yeah. So yes, but thanks for that.
Yeah.
Okay.
So Bruce is saying he'll reach out directly.
Okay, sounds good.
Yes. I have one question. Since you're writing your book on AI ethics, how can we stay in touch with you? How can we connect and get the book or know more as your?
Yeah, I think connect with me on LinkedIn. I'm very active on LinkedIn. You can send me private messages on LinkedIn. And if you want specifically, I can share my email, but LinkedIn is the best way. I'm there. Subscribe to my YouTube channel. I'll be posting more.
Yeah, share that.
Thank you, Sudha. But as obviously going through traditional publisher, they have their rules. I cannot start marketing book yet as I'm writing. And once they give the go ahead, maybe I think early spring next year, I'll have more, I'll be all over with my marketing the book. So right now I'm enjoying or discovering the process of writing a book, working with the publisher, working with editors. But I post content every week. I upload YouTube videos every Tuesday. So please connect on LinkedIn and subscribe to my YouTube channel. Thank you so much, Sudha.
So before you go, can we ask you one question related to, I'm not plugging in our book. This is not a setup question, guys. It just came to me because we just did the career pivot to AI ethics. Specifically in healthcare, you started out in the beginning saying we also look at whether there are ethical consideration. It becomes a big deal in terms of data, because there was recent research about how clinical trials were done and a certain population was left out and things like that. Is that seriously being considered in industry when you're looking at data, doing feature engineering? Is there even one of the steps in the data science process to look at whether the data is unbiased, whether it's representative of all populations and bias?
In a nutshell, for all industry sectors, not so much, but healthcare is the most, because healthcare is already holding their feet to the fire with PHI and HIPAA. So mostly what I notice in healthcare is de-identified information. You do the algorithm on publicly available data sets, you don't do it, and then you give the hospital the algorithm, they will run it themselves. So that's in a nutshell, but it's a whole, I can dig deeper into what is happening in terms of other avenues as well.
This is fantastic. And, I'm sure we'll bring you back if we can find your time, because you've got us, good speaker gets us thinking about all the stuff we don't know. So you got us excited about it. So thank you so much.
Thank you. Got to run.